Hello everyone, my name is Srihar Joshi and I'm deeply honored to present our research to you today. Our presentation focuses on machine and deep learning models for stress detection using multimodal physiological data. I'm joined in this research by Professor Dr. Iman Abdel Fattah from the School of Computer Science and Engineering at Sacred Heart University and Shrika Tiwari, an electronic engineering major from Institute of Engineering, Tribhuvan University, Kathmandu, Nepal. I'm excited to share our findings and insights with you. Stress is an unavoidable part of daily life that impacts individuals in various ways. While moderate stress can be managed, chronic stress poses significant threats to well-being, potentially disrupting daily activities and diminishing performance in critical situations. Chronic stress is linked to numerous health problems, including cardiac arrests, depression, and a weakened immune system, which can increase the risk of severe illnesses like cancer. In the workplace, high stress levels are a major concern, with many workers seeking improved stress management strategies. An automated stress detection system can offer timely interventions to address these issues. Physiological signals such as electrodermal activity and heart rate variability are reliable stress indicators reflecting the body's response to overwhelming demands. These signals can be monitored using sensors on various body parts and are well suited for integration with wearable devices. However, achieving accurate stress detection often requires numerous sensors and features, leading to substantial processing demands. Optimizing these systems for efficiency is crucial for effective and swift analysis. This research uses both traditional machine learning models and deep learning models to detect stress from pre-processed physiological data, evaluating their performance using the WSAT dataset. Our research employs 7 traditional machine learning models: logistic regression, Gaussian naive Bayes, AdaBoost, XGBoost, decision trees, extra trees, and random forest, and 3 common deep learning algorithms: deep neural network, convolutional neural network, and recurrent neural network. These models are trained and tested using sensor data from the WSAT dataset, which includes multimodal physiological signals recorded during various affective states such as baseline, stress, amusement, and meditation. This research is conducted in 2 phases. Phase 1 involves training models on data from a randomly selected subject and testing on the remaining subjects, while Phase 2 involves training and testing on combined data from all subjects using an 80-20 train test split. Both phases analyze chest and wrist data to evaluate the efficiency of the models under different conditions. The key contributions of this research include a comprehensive evaluation of both machine learning and deep learning models for stress detection, utilizing feature engineered categories shown in the figure on this slide from raw human activity recognition data. There's the inclusion of all 4 stress categories from the WSAT dataset, which are baseline, stress, amusement, and meditation, to assess model performance. A comparison of models using both wrist and chest data, in contrast to earlier research works that often focus solely on chest data. And lastly, an evaluation of 2 different data utilization approaches: training and testing on the same set of subjects versus training on one set and testing on a separate unseen set. The WSAT dataset features raw sensor data from 2 devices: RESP-BAN, a chest-mounted device, and Empatica E4, a wrist-worn device, collected from 15 subjects. The RESP-BAN sensor, sampled at 700 Hz, provided data on ECG, EDA, EMV, temperature, acceleration for 3 axis, and respiration. The Empatica E4 device recorded acceleration at 32 Hz, BVP at 64 Hz, EDA at 4 Hz, and temperature at 4 Hz. In Phase 1, 10 subjects were randomly selected, and their pre-processed data was used to train the algorithms. The algorithms were evaluated separately on the chest and wrist data. The F1 scores for various classifiers on these data are shown in figure on this slide. And as we can see, the RNN achieved the highest F1 scores for both chest, which was 80.4%, and wrist data, which was 93.5%, whereas the Gaussian NB and AdaBoost recorded the lowest F1 scores of 24% and 46% for chest and wrist data respectively. The training and testing times for neural networks, as evident on the figures on this slide, was significantly longer compared to traditional machine learning models. The RNN required the most time, taking 384 seconds for chest data and 600 seconds for wrist data, while the Gaussian NB was the quickest, needing only 0.06 seconds for chest data and 0.09 seconds for wrist data. In phase 2, the pre-processed data for all subjects were combined and split into training and testing sets with an 80-20 ratio. Separate train and test evaluations were performed for chest and wrist data. The F1 scores for various classifiers are shown in figure on this slide. The XGBoost classifier achieved the highest F1 scores of 99.8% for both chest and wrist data, while the Gaussian naive Bayes classifier had the lowest F1 scores, which were 39.1% for chest data and 50.1% for wrist data. Consistent with phase 1, neural networks required significantly more time to train and test compared to traditional machine learning models. As illustrated in the figure, the RNN had the longest training and testing times of 564 and 614 seconds, whereas the Gaussian naive Bayes classifier was the fastest, taking only 0.13 and 0.24 seconds for chest and wrist data respectively. This slide presents the confusion matrices for both phase 1 and phase 2 of our research. On the left side, you'll find the matrices for phase 1, and on the right, those for phase 2. In phase 1, the confusion matrices for the RNN model show a higher density along the diagonals for both chest and wrist data, indicating better class prediction compared to the poorest performing algorithms, which were AdaBoost classifier for chest and the Gaussian NB for wrist data. In phase 2, the XGB classifier also demonstrates higher diagonal density, reflecting superior class prediction performance compared to the poorest performing classifier, which was Gaussian NB. To sum up, this research utilized the VSAT dataset, which includes raw sensor data from ResviBand and Empatica E4 devices to assess the performance of various machine learning and deep learning algorithms for stress detection. The study was conducted in 2 phases. In the first phase, features extracted from the sensor data of 10 randomly selected subjects were used to train and test several classifiers on chest and wrist data separately. Results showed that recurrent neural network achieved the highest F1 scores for both chest and wrist data, though it required significantly more time for training and testing compared to traditional machine learning models. The second phase involved training on data from all subjects and applying an 80-20 train test split. In this phase, the XGBoost classifier achieved the highest F1 scores for both chest and wrist data, while the Gaussian naive Bayes performed the worst. Similar to phase 1, neural networks, particularly the RNN, took considerably longer to train and test compared to the machine learning models. In phase 1, the RNN excelled in predicting stress categories for new subjects. However, in phase 2, traditional machine learning models, especially the XGBoost classifier, performed better when trained and tested on the same set of subjects. Future research will focus on techniques like regularization, ensemble methods, and hyperparameter tuning to improve the generalizability of machine learning models. Additionally, optimization techniques such as early stopping, learning rate schedulers, and distributed training will be explored to enhance the efficiency of deep learning models in terms of training and testing time. Lastly, the references for this research are shown in the current and the following slide.